this is what we get. For the potassium, only 3% of substitutional defects. Only 3%. For the rubidium, 8% of substitutional defects. Much less than before. But that was enough to see this effect, this phenomena. Here, KH is very small because these values are much higher. Here, we don't even see this term, KH, in the experimental data. We cannot even see it because the data in the rubidium is 10 times higher than in the potassium. So rubidium is like a magnifying lens, like an amplifier of the phenomena. And we use a lot of magnetic fields, but you see, the phenomena saturates at only 3 oester. And here we went very low. We went to 0.06, 6 millioester. We couldn't move a chair, a metallic chair in the lab, because any metallic chair we move, the cryostat, anything we move, change the magnetic field at our sample site. We have to compensate the magnetic field at the sample site and don't move. Just keep measuring, okay? We had to measure in the night. For this and for other cases that is even more difficult. In the night. And we knew when 7 in the morning was. We didn't need the watch because the technician for the cryogenic, just to produce liquid helium, was very punctual and always arrived at 7. He was arriving by car, and he was parking the car close to the laboratory. The laboratory is in the basement in order not to have vibrations and so on. And our measurements stopped because the car, about 100, 150 meters away from the sample, was producing a perturbation of several millioester. So, now you see the same phenomena, same problem. Let's correct for KH. So, and now I will go faster. So we correct it. We have the collapse. And then again, we can mix rubidium and potassium, and we have this collapse. Here we have some problems. These were due to the very, very diluted samples, where some defects, lattice defects, were also producing some problems. And this is the most difficult area to measure. But in general, the points collapse in a single curve. So this is the general data collapse. And here, we could also include the manganese fluorine system, but I will show you later. We went to another one. Now we changed one thing. Instead of being three-dimensional, we are very isotropic, but with some low-dimensional character. Is this compound, which this is kind of a linear change of manganese. Manganese can be substituted by cadmium because the crystal lattice of the cadmium derivative is the same as this manganese. So no structural problem in the substitution. And we needed very, very low substitution, only 0.8%, less than 1%. With less than 1%, we had a huge effect, a huge effect. Forget this phenomena, this shoulder. We explained it, but it's complicated, and we have no time to go into these features. But here you see, you still don't see it? No, because I didn't include. We were measuring even at 3 millikelvin in the millioester in this case. Again, everything collapses. And here we collapse all the data sets. manganese fluoride, the iron derivative, both, this manganese linear chain, everything collapsed very beautifully. So that tells us that the phenomena is strictly related to the antiferromagnetic lattice and not to the compound. So is dilution independent, field independent, compound independent. This is a list of compounds where this phenomena has been observed, and probably there are many more, but nobody has taken the interest. I have to tell you, we measure all this, and we did not measure this one. We did not study this one. This was studied by a Japanese group. They just had the anomalies observed, and when we published the papers, they went to the papers, and then they reanalyzed the anomaly, and it fitted very well with the universality law. To the summary. Spontaneous magnetization appears below Tn. It is related to the antiferromagnetic origin. It is caused by effects due to substitutional disorder, and it is qualitatively independent of the applied field value of X and of the compound. The differences are only by a scale factor. This is the facts we have observed. Possible, well, we have to understand it. You go to the library, read papers, and excess magnetization has been observed in random fields, volume effect in antiferromagnetic domains, piezomagnetism. And as I told you, let's exclude weak ferromagnetism because this is not a case for weak ferromagnetism. We are not measuring in the perpendicular direction. And we took very good care to align the crystal parallel to the applied field and in the direction of the antiferromagnetic alignment. So these are possibilities. So we have to look whether this is at the origin of our phenomena or not. So random fields. Random fields appear rather high magnetic fields are produced in diluted antiferromagnets generated by the applied field. Then it's highly diluted, and the system is trapped in some metastable states, non-equilibrium domain, but you need a big field, much higher than the fields we are talking about. Also, this dependence of the magnetization with random field is proportional to a power of the applied field. So the increase of the magnetization is proportional to h to a given exponent, close to 2. This is not our case. In our case, it did not depend on the applied field. We saw it. So we can exclude this origin. Volume effect, what do we mean by that? This is if we have a sublattice A, sublattice B going down, and now we randomly substitute some sides. Well, maybe we do not substitute 50% of A and 50% of B. Maybe we substitute 48, 52. So there is a kind of a standard deviation. The standard deviation is going to produce an excess of magnetization because one sublattice has some few moments aligned in a given direction more than the other one. You made the calculation, and we made the estimation of how much you expect, and then compare with your results, and we find that we are 1,000, 10,000 times, 3-4 orders of magnitude higher than the standard deviation, the magnetization expected from the standard deviation. So